And this is roughly going to be the outline of our next 7 lectures. So, so far you've learned about the quantum field theory of spin-zero particles in terms of scalar fields, scalar quantum field theory. However, fortunately for us, the universe is composed of particles with spins higher than spin 0 as well. And you and I would not exist if there weren't spin-half particles. We are mostly made out of spin-half particles held together by spin 1 particles. So it turns out scalar fields or even vector fields and tensor fields are not suitable to describe spin-half particles. Before they're described by a mathematical object called spinors. And in today's lecture and tomorrow's lecture, we are going to explore the classical theory of spinors. You might say, why are we exploring the classical theory of spinors when this is a course on quantum field theory? The idea is that the properties of spinors, even classical spinors, are important in constructing Lagrangians and equations of motions, which we then will quantize. So we actually need to know something about the classical theory of spinors. My treatment will not be very rigorous, but I hope to give you a somewhat intuitive, but I think somewhat complete picture of classical spinors. Okay, before we delve into the spinors, so this is our brief outline, classical theory of spinors today and tomorrow. And that'll include how to construct Lagrangians, and from the Lagrangians, how we construct we get the equations of motion. And for the quantum fields, we'll actually need to know the solutions to the free classical equations. So we'll actually study them as well. And then we'll quantize the spinors, probably on Monday. And then construct the fermion propagator. And then the next day, we'll construct our first interacting theory of spinors, which will be the Yukawa theory of nucleons. And this will be a theory of fermions interacting with each other by exchanging massive scalar field, scalar boson. And then in that context, we will develop the Feynman rules for fermions. And then after that, we'll move on to even higher spin to an electromagnetic field, which describes a massless spin 1 particle. And we'll do a quantization which will be covariant in its nature. There are many different ways of quantizing electromagnetism because of a certain quote-unquote symmetry it has, called gauge symmetry. But the quantization procedure that we will choose is the covariant quantization. And from that, we will move on to QED, which you all know is the theory of electrons and positrons interacting with each other via exchange of photons. And then for this course, we'll stick to the tree-level QED. There will be a few supplementary lectures at the end of November where we will treat some of the one-loop phenomena of QED. And then we will work out some cross-sections. The cross-sections are what you observe in scattering experiments. When we go to the Yukawa theory of nucleons, I will try to give a brief overview of the LSZ formalism for a spinor. Not in a technical way, but in a way that I hope will illuminate why each component in the formula, what they mean. All right? Please feel free to interrupt if the question is very involved and if it takes too long to answer. I'll probably have a discussion outside of class. But if it's not, then I'm happy to engage and answer. So, all right, any questions? All right, so classical spinors then. Oh, by the way, I probably don't have to tell you that the particle that you get when you quantize a spinor field is a fermion. So you probably know that already. So, okay, classical spinors. So spinors are kind of new. They're kind of a new representation of the Lorentz group. So the Lorentz group, I will write sometimes as O1,3. And what this tells you is that the Lorentz group consists of all matrices lambda such that lambda satisfies this relationship, where eta is your space-time metric in the Cartesian coordinates. It's a Minkowski space metric, and in this course we will choose this to be the signature. Okay. So this is what we call the Lorentz group. Now let's remind ourselves what a scalar is. So a scalar is if you make a Lorentz transformation on your space-time, then a scalar field phi is one that transforms in this way. The phi of x goes to phi prime, a new scalar field. And if you evaluate this phi prime at the same space-time point as x, same numerical value as x before, then you get just the same thing, but now the argument is shifted. So because there is nothing apart from the argument, there's nothing dressing the scalar field under this transformation. In a sense, the scalar field is invariant. So in GR, you saw generalization of the scalar field to vector fields. So a vector field, for example, would transform in a way where you would actually have a factor of the Lorentz transformation acting on the vector field. And then you can have arbitrary rank tensor fields. So for example, we can take a rank 2 tensor field. And under the Lorentz transformation, this will go to so this is a vector field, which is a special case of a tensor field. And this is a rank 2 tensor. Okay? So spinors do not fall into this category. You cannot express the transformation properties of spinors in this way. So how do you express spinors? So we're going to actually derive how spinors transform from the Dirac algebra. So the Dirac algebra has this form. In 4 dimensions, there are 4 gamma matrices, and they satisfy this algebra, where this is an anticommutator. So the definition of the anticommutator is like so. Remember that commutator had a minus sign here. The anticommutator has a plus sign. So this is known as the Dirac algebra. And I'm assuming that you're familiar with it. Anyone here who is not familiar with the Dirac algebra? Okay. So just give you a brief history of where the Dirac algebra came from. So Dirac, in 1928, proposed an equation for electrons. And what he did is that he wrote down the Dirac equation, which is now known as the Dirac equation. And this equation had this form. So it was first order in time because Dirac wanted to mimic the nice probabilistic interpretation that Schrodinger equation has. But he also wanted to have relativistic covariance. So if he wrote down first order in time, he had to write down a first order in space equation. So, okay, let me just, sorry. This is what I mean. So there's an implicit sum over repeated indices. So this is the Dirac equation. But the quantities gamma, Dirac just wrote down as some unknown quantities. To figure out what the properties of gammas should be, Dirac imposed an additional constraint on this equation. He said that, I want this equation to describe free particles. Not only that, I want these particles to be relativistic, therefore they should satisfy E is equal to square root of p squared plus m squared. So he couldn't actually do that. He did the next best thing. The next best thing was that he imposed the condition that the solution, plane wave solution of this equation would actually be would satisfy the square of the energy mass relationship. And the way he did that is that he imposed that psi of x also be a solution to the Klein-Gordon equation. So he said that there should also be a solution to the Klein-Gordon equation. So I'm writing out, just for history's sake, all the factors of C's and H bars, but for the rest of the course, I will set them to 1. So he imposed this. And so you can actually derive this equation from this equation by applying this differential operator with the mass, but with a positive sign. If gamma mu's satisfy this. Now, you can this is like 2 lines of algebra, so I'm not going to derive it for you. But I encourage you that you can show that this equation follows from this equation if the gammas satisfy this algebra. And that is how Dirac derived the Dirac algebra. And there you go. So these gamma mu's, Dirac found out the smallest representation that you can get for these matrix representation that you can get for these objects is that they were 4 by 4 matrices. And therefore, Dirac's wave function was a 4-component object. But this 4, as we shall see in this lecture, has nothing to do with space-time. At least it's not the 4 of space-time. Okay? Okay, so that's our blitz review of the Dirac algebra. So from the Dirac algebra, what we will do is that we will derive a representation of the Lorentz group. Okay? Sorry, my approach here is a bit formal, but I think that having a formal machinery in mind will allow you to construct different kinds of theories. So I'm giving you the Lego blocks by which you can construct different kinds of quantum field theories. Okay, so if we now look at the 0 component of the Dirac algebra, that means what it tells us is that the 0th component matrix is squares to 1. So that implies that gamma 0 is Hermitian. But if you take the spatial components of the Dirac algebra, we get equal to -1. And then that implies that the spatial components are anti-Hermitian matrices. So of course, this depends on our choice of metric tensor. our convention, if we had chosen the mostly plus convention that people in GR and string theory use, then these roles would be reversed. Right? So I presume that you had some introduction to the Lorentz group in the front end. Yeah?
You have also imposed a unitarity condition?
No, I have not imposed any unitarity conditions.
So don't you get inverse gamma matrices instead of the Hermitian condition?
Right. So if I say, so the eigenvalues of this guy is, say, A, then I get acting on some vector, right? And this is basically telling me, so that means that A squared is plus minus 1. So that means my eigenvalues are real. And if my eigenvalues are real, then the matrix has to be Hermitian. So, and same with, because the eigenvalue squares to minus 1, so the matrix has to be anti-Hermitian. OK, so you guys had some introduction to the Lorentz group, right? So those of you who haven't, so let me just write out the Lorentz transformation matrix explicitly, because we will need how that's done. Because it's kind of important enough, let me write it out in a new board. Okay. So a typical Lorentz transformation matrix, which is in the connected part of the Lorentz group. So here I'm assuming that this is actually in the SO1, 3 part of O1, 3. So there are some discrete transformations which are not contained here that are contained in O1, 3. And I'll come back to those in the next lecture. But the Lorentz group has this form. It is an exponential. We are expressing it as an exponential. And these are the parameters of the Lorentz group. And if you remember, in 4 dimensions, there are how many parameters in the Lorentz group? 6. 3 boosts and 3 rotations. So, but here, omega, alpha, and beta take the values from 0 to 3. So, it seems like there are 16 components. But these are antisymmetric. We impose antisymmetry, so that cuts it down to 6 independent components. So, and the omega 0 I, these are the boosts, and omega ij, these are the rotations. And the m's, these are the generators. So m0i is equal to minus mi0. Note that these are just labels. They are matrices. They are 4x4 matrices, but I'm suppressing the matrix index here. So these are the generators of the boosts in the xi direction. So these are boosts in the xi direction. And these are the generators. Again, they're antisymmetric. These are the rotations in xi, xj plane. So for the rest of this lecture, for the next 20 minutes or so, let's assume that the space-time dimension is actually D. And you might say, why do we want to do that? We live in 4 space-time dimensions. I'm happy living in 4 space-time dimensions. But it's actually very easy to figure out the properties of the representation of spinors in general space-time dimensions. So we will actually assume for most of this lecture that D is actually like an even integer, an even positive integer. So if the dimension of space-time were D, then how many independent Lorentz generators would there be?
D times D minus 1 over 2.
Right, because it'll be an antisymmetric, so it'll be half times D, D minus 1. So the Lorentz group in D dimensions would have this as its dimension, right? Because the number of independent parameters you have in this formula tells you the dimension of the group. That is the definition of the dimension. Okay? So this is the expression for the Lorentz group. And you can even find out what the explicit form of the generators are. So now I have to give you the matrix elements of the generator. So I'm taking the alpha beta generator and its mu nu component. And you can show that this is the explicit expression for the generator. I write this out, this unwieldy looking expression for the generator, because you can use this expression to prove the Lie algebra for the Lorentz group. The Lorentz group, SO1, 3, or this actually has a special name called the orthochronous proper Lorentz group. Proper means that it's the determinant of all the elements here are 1, and therefore they're all smoothly, continuously connected to the identity operation. And orthochronous means that the 0, 0 component is positive, so that when you apply a Lorentz transformation, the arrow of time does not flip. There are elements in the larger Lorentz group, O1, 3, which are non-orthochronous, such as parity, their reflection in space, and time reversal, which flips the arrow of time. But those elements cannot be expressed in this way. They are not connected continuously to the identity. By the way, guys, around 50 minutes or so, we'll take a short break. I'll tell you when it's due. So, okay, coming back to our orthochronous proper Lorentz group, if using this expression for M, you can derive the Lie algebra for the Lorentz group, known as the Lorentz algebra. And bear with me, this is one of those things that I don't enjoy writing out, but needs to be written out for the sake of completeness, not only once, but twice, actually. And every year I make some mistake in writing this out. So this is the Lorentz algebra. And using the machinery of Lie algebra, which is not very sophisticated machinery, you can show that this is just the infinitesimal version of this expression, where in lambda lambda transpose, you plug in this and expand to small orders in omega. Okay? So now, if we can find some way of constructing generators using the gamma matrices, which reproduce the Lorentz algebra, then I will have proven that the Dirac algebra contains a representation of the Lorentz group, right? So all we need is that we need to construct some version of these generators, but now constructed out of the gamma matrices. And the answer to that is very easy. So the spinor version of the generator, so the spinor version of the Lorentz generators are, we call them sigma mu nu, and they're defined to be this. Note that they are not necessarily Hermitian. Okay? So how do you prove that? So I'm just going to give you some outline, and you can do it yourself. And it's actually good to do once in your life. It builds character. I haven't done it. No, I actually have. It's a necessary condition for building character, not sufficient. So first, show that the commutator of sigma with a gamma matrix is so this equation actually has a geometric meaning, but I will come back to that in the next lecture. So that's easy to show, and then once you've done that, you can use this and you can expand one of these sigmas in this equation and then expand it out so that you can express the whole thing in terms of commutators of this commutator. And what you get, can anyone guess what you get? Right. So you get exactly that expression, which I will call dagger. So you get the right-hand side of dagger. I don't want to write that out again. But with m replaced by sigma. Okay? So, which means that the Dirac algebra has within it a representation of the Lorentz group. Yes?
How can we show that this is not a representation of the tensorial form?
Yeah, we'll show that, yeah. That's a good question. So actually, it's not, if you now write out what the finite version of the Lorentz group is, so these are the generators. So how would you write out the finite version? So S, A, B are the matrix element. And it'll depend on an underlying Lorentz transformation. And it'll be minus I by 2. Omega is that's the parameter that parameterizes your Lorentz transformation. But now what we have done is that instead of m, we have just replaced m by sigma alpha beta. And this is some matrix, and we're taking the AB component of this, right? So this is the finite version of this new representation of the Lorentz group. And it turns out this is actually not exactly the Lorentz group, although the Lie algebra is the same. This is an element of what is known as a spin 1, d minus 1 group. And the spin group is a double cover of the Lorentz group SO1, d minus 1. Which means that for each element in the Lorentz group, there are two elements in the spin group. So if you construct a map from the spin group to the Lorentz group, there'll be two elements which will map onto the same element in the Lorentz group. And this is entirely analogous to something you already know. You know that SU2, which you love from quantum mechanics, hopefully, is a double cover of the rotation group in SO3. And let me remind you how that worked. The way it worked is that you took the three-dimensional vector and you dotted it with the three Pauli matrices, and you took an element of SU2 and you did a similarity transformation with that SU2, and then you took another Pauli matrix, multiplied the whole thing, took the trace, and that up to some number was the rotation, 3 by 3 rotation matrix of SO3 acting on your three-dimensional vector, right? So this is how you construct the map from SU2 to SO3. Now you see this map contains two factors of SU2 in these matrices on the left and one factor of SO3 on the right. So if you replace U by minus U, which is also an element of SU2, because SU2, if you think about it, then you see that those two guys map onto the same element in SO3. So this is a 2-to-1 mapping, right? So the mapping between the spin group and the SO group is exactly analogous to that. This is just a side comment. We won't really need this. So now, yeah?
But does that mean that physics have actually a bigger symmetry group than the Lorentz or Poincare group due to these schemes?
Bigger. Yeah, this actually just kind of mostly matters. Yeah, no, I mean, I don't know if it's a symmetry group. I wouldn't think of it as a symmetry group. But some very, okay, we won't use this directly, but of course this is very important. Because, the stuff that you know about spinors, that, a spinor wave function for an electron, you can actually, if you apply a 360-degree rotation, it doesn't come back to itself. It comes back to a minus of itself. That's actually related to this. So yes, it's extremely important. Yeah. So, but I don't think, but when you say symmetry group, that has a very specific connotation in physics. You're saying, and I don't. In some sense, you're right. Yeah, because if you think of the Lorentz group as the symmetry group, space-time symmetry group, then the spinors do have like a bigger. Yes, I think I agree with you, but also I wouldn't put it in those terms. But yeah, you're right. Yes, Nick.
You think your symmetry group is actually bigger than just different? Because you have to
yeah, exactly.
Spin rotation.
Yeah, I think. Yeah.
Space-time rotation.
Yeah, I think that would be a better way of saying it. It's a different because the bigger thing would be if you. So yeah, we'll see an instance where the symmetry group is actually bigger. So for example, our symmetry group for the simple theories are actually O1, 3 if you look at just the Lorentz part. And that's actually bigger than SO1, 3, although the dimensions are the same. The volume is bigger because there'll be discrete elements multiplying it, right? So there's an instance where you could say that the symmetry group is bigger. But there are instances where where parity is broken and stuff like that is broken when it's actually not bigger than SO1, 3. Okay, so now so far it's been very formal, but formally we have proved that the Dirac algebra contains in it a representation of the Lorentz group. So now let's ask ourselves what are the dimension of these matrices S, right? Because we need that. Because these matrices S will be acting on spinors. We need to know what the dimension of the spinor is. So these are some square matrices, and the spinors will be column matrix of that same dimension. So let's ask that. So we can actually do better. We can actually derive the whole thing. Is this broken? So what we can do is that we can take our D Lorentz, our D Dirac matrices and pair them up as creation and annihilation operators. So we have paired them up. So you can verify that these are k plus 1 pairs of creation and annihilation operators. Okay, what is k? So just reminding you, we are assuming that D for the time being is even. We are living in some arbitrary even dimensional space-time. So we can express D as 2k plus 2. And this k is defined in that way. So here, I goes from 1 to k. So we have k plus 1 pairs of creation and annihilation operator, but they are fermionic creation and annihilation operator. There was a small exercise in yesterday's tutorial about fermionic creation and annihilation operators. Did you guys get to do it? How many of you got to it? Okay, about maybe half the class. Okay. So what do I mean by fermionic? That means that you can show, okay, before we do that, by gamma A, I mean all these guys. So A takes the value from 0 to k. And by using the hermicity property of the Dirac matrices, it follows that the Hermitian conjugate, if you take the Hermitian conjugate, you basically just flip the sign here. And the fact that they are a Dirac algebra, so using the Dirac algebra, you can show that they satisfy this, and so the anticommutator of plus and minus gives you this. But if you take the anticommutator with a plus plus or an anticommutator with a minus minus, they give you this, right? So let me quickly give you an aside on what does it mean to be fermionic creation operator, creation annihilation operator. For those of you who haven't done yesterday's, I won't do the detailed calculation. You can go back and do that part of the tutorial. It takes maybe 10 minutes. So the idea of a fermionic creation annihilation operator is, suppose you have an operator A and A dagger, and they satisfy this relationship, and these then you can construct a number operator, and by using these, so this is Hermitian, so it has real eigenvalues. And the number operators using these relationships, you can show it just squares to itself, which means that its eigenvalues are 0 and 1, And because the number operator eigenvalue is 0 and 1, it's only 2 eigenvalues, occupied or not occupied. That's why it's a fermionic number operator. And then you can show that for these guys to have the interpretation of a ladder or a stepping operator, they must satisfy the usual commutation relationship. So you can show that they satisfy what you would expect from a set of creation and annihilation operator, right? So what we have done here, we have constructed a k plus 1 pair of these things, right? And remember that a dagger, because because of this relationship, a dagger squares to 0, right? For this relationship means that a squares to 0, right? So that means that any fermionic creation operator you can only apply once. If you apply twice, you're screwed. You get 0. So you should have a picture that if you have k plus 1 pair of creation operator and you had some lowest weight state, how many times can you apply the creation operators with impunity? K plus 1 times, right? If you take any one of those creation operators and apply them twice, you're going to destroy that state. So any lowest weight state on which you can apply the creation operator, you can apply each of these creation operators once or not at all. So in total, you're going to have 2 to the power k plus 1 states, right? So let's, so by the way, for each pair of these creation and annihilation operators, you can construct a number operator, which is constructed in this way. And this you can show has eigenvalues plus half or minus half. I've just subtracted half so that instead of this guy having 0 and 1 as the eigenvalue, it now has eigenvalue plus half and minus half, right? So let's construct a k plus 1 dimensional vector which collects the eigenvalues of these things. So these eigenvalues we call S0, S1, sk. And each of these can be either a plus half or minus half. So it's a k plus 1 tuple of plus minus half. I'm just formalizing what I've just said. So the details are unimportant. What's important is that we are keeping track of the dimensionality of the vector space. So the lowest weight state is the one where all these s's are minus half. Okay? And it's defined by being annihilated by all the lowering operators for all A. Then any arbitrary state, as I've said, it will be labeled by the k plus 1 set of integers. It will have either the creation operator acting on it. If it does act on it, then the value of sk would be half. If it doesn't act on it, the value of sk would be minus half. If it is minus half, plus half is 0, so this guy drops out. So this is just a clever way of writing out. And then, so I'm all the creation operator acting on this lowest weight state. So this is our general state. Okay? So as I said before in words, each of these creation operator, either they're there or they're not there. So how many possibilities do we have? Again? Louder? 2 to the power k plus 1, right? So that is the dimension of our representation. Okay? That is the dimensionality of the vector space on which those matrices S that we constructed will act. Break time is near. So, so we have a 2 to the power d minus by d by 2 dimensional vector space. And this vector space and element we call psi A. We're not considering space-time dependence, but so you can think of a spinor field as a vector space like this at each point in space-time. Just as the scalar field was a zero-dimensional vector space. So here A takes the value 1 to d by 2. Okay? Sorry, 2 to the power d by 2. And in 4 dimensions, this is 4, which is exactly what the Dirac spinor is. You know that the Dirac spinor in 4 dimension is 4. But now you know where it came from. So the other thing is that this representation is complex. And that's because the gamma matrices themselves are complex. And the S matrices that we construct there will in general be complex. So they will act on this spinor field on this object. So then this better be complex. So this is complex. And this vector space, we call it physicists call it a Dirac spinor. Okay, so we have just constructed abstractly our first example of a spinor. So this is a finite dimensional representation of the Lorentz group. And therefore, it is not unitary. There is a theorem in group theory which says that if you have a Lie group which is non-compact, like the Lorentz group, its finite dimensional representation cannot be unitary, which is bad news for quantum mechanics, but we are not doing quantum mechanics, we're doing quantum field theory, because this size, this finite dimensional vector space, all the objects in it, upon quantization will become operators who will act on some infinite dimensional Hilbert space called the Fock space, which will represent the arbitrary number of particles with arbitrary momenta. That vector space that this will act on upon quantization is infinite dimensional, therefore it can be unitary, but this thing is not unitary, right? So now the question is this representation reducible or not? And we will find that out in 5 minutes. So we ended the last part by asking a question whether the Dirac representation, which is psi A, whether it's reducible or not. And the answer is, what is the answer?
Yeah.
It is reducible?
Yeah.
Yes. Anyone for not reducible? Okay. Okay. So it is reducible, and how do you show that? You define an operator matrix, which we call, for historical reasons, gamma 5, and its formal definition is this. Which you can show is this. And then using the Dirac algebra, you can show that gamma 5 squares to 1, and that gamma 5 is Hermitian. So this means that its eigenvalues are +1 and -1. And very importantly, gamma 5 commutes with all the Dirac matrices. Anti-commute, sorry. Now, sigma, these are composed of two gammas, remember? So gamma 5 then commutes with the generators of the Lorentz, of the representation of the Lorentz group, which means that gamma 5 will commute with all the S matrices here. So there's a lemma in group theory called Schur's lemma. And Schur's lemma tells you that, so if A is a matrix that commutes with all the representations, so all the matrices of an irreducible representation, then A is just proportional to the identity. Okay? In this case, you can verify that gamma 5, although it commutes with all the matrices of a representation, it's not an identity matrix. And therefore, the representation whose matrices it is commuting with cannot be an irreducible representation. So this shows that the Dirac representation is not irreducible. Yes, is not irreducible. So what are these smaller components? So this is oh, by the way, those of you who are Waterloo students but not SAI students, I will collect your emails from Debbie after the class today, and I will include you in all the upcoming emails. I didn't know your emails before. So this lecture note and tomorrow's lecture notes are already up on the SAI wiki. So sorry, I should have told you before, you don't have to actually take lecture notes. So, somebody complained in last week's feedback that the lecture is just reading out from the lecture note. I think that is the point in some sense, but you don't have to actually take lectures notes, okay? Although my lecture notes will be a little different from what I say in the class, so. So yeah, you don't have to. You don't have to take lecture notes if you don't want to. Okay, so so we have the space of Dirac spinors. And then it has a subspace which is labeled by the +1 eigenvalue of gamma 5, and they're called left-handed Weyl spinors And the -1 is called the right-handed Wal spinners. So we can construct projection operators which will project our Dirac spinner onto the left-handed or the right-handed part. And the projection operators are given by this. The left-handed projection operator is minus this, and the right-handed is given by this. And you can verify that they're projection operators because Pi Pj is delta Ij Pj, and that they sum up to the identity. So, and then a left-handed Wal spinner, which we denote by psi L, can be gotten from the Dirac spinner just by applying P of L on a Dirac spinner. And a right-handed Wal spinner in this way. Okay? So for the rest of this class, I will give you an explicit representation of the Dirac matrices and all the spinners. You know, this is very useful for calculation, and we'll use this for the rest of the course. And in the standard model course that you'll have, it will use exclusively this representation, because this representation uses the Wal spinners are the natural objects in which all the symmetries of the standard models are manifest. Okay, any questions so far? Okay. So, you know, I'm going to make an obvious statement, but from experience, I know that sometimes the obvious statements are things that, you know, sometimes you miss. So the idea is that so far, what we have done is that we take some Lorentz transformation, which means we take some space-time and transform the space-time like so. And that means that there is some spinner field living on that space-time which transforms according to this rule. Okay, this is what we have done so far. We have constructed these S's. These S's are a representation of the Lorentz group, and that's why these S's are functions of lambda. And these S's are constructed from exponentiating those sigma matrices which are hidden, which I probably have erased. Okay? And they act on some vector in the vector space sense, which are called psi. And the dimension of these guys are 2 to the power d by 2. And the dimension of these is 2 to the power d by 2 times 2 to the power d by 2. Okay? Yeah?
You defined the S Lorentz representation in terms of the gamma matrices, but
right.
You did not connect them with the lambda?
Yeah, the lambdas, okay. Yeah, each element lambda is parameterized by omega, the parameter. So that parameterization is there, right? Because if you look, see, that there's the omega. Yeah. Okay, so let me give an explicit basis called the, for the Dirac matrices called the Weil basis. It's also known as the chiral basis or representation. And it's defined by the basis in which your gamma 5 is diagonal. So you can always, do similarity transformation and change your matrices, but in some basis, your gamma 5 will have this form. So in terms of 2 by 2 matrices, right? And the basis in which gamma 5 has this form is known as the chiral basis or the Weil basis. And this is a very, very useful basis that's useful for most computation that you will come across. But there are a lot of other bases too. This is not the basis that Dirac first proposed, or this is not the first Dirac's representation. So in the Weil basis, the gamma matrices have this form. Gamma 0 is, again, these are block diagonal matrices, and the spatial parts are conveniently expressed in terms of Pauli matrices. So to show that gamma 0 and gamma I satisfy the Dirac algebra, you have to use the Pauli algebra for this, okay? I'm assuming that you know the properties of Pauli algebra. You can just Google them. So to write out things more compactly, let's introduce a notation. So it's kind of a Four covariant notation, meaning it's not real covariant, which is sigma of mu. So mu goes from 0 to 3. The first component, the 0th component, is an identity matrix, 2 by 2 identity matrix. The other 3 components are just the 3 Pauli matrices. And then sigma bar of mu is, so there's a minus sign here. So that's a notation. Okay, so in this notation, we can express all 4 gamma matrices in this form. Okay. Now, in the Weil basis, a Dirac spinner has this form. Its upper 2 components is a left-handed Weil spinner, and its lower component is a different right-handed Weil spinner. What do I mean by that? Remember that we define psi L to be P of L, psi of D. So if you now plug in the explicit expression for psi 5 in PL, and if you plug in this, you basically get this thing, right?
You wrote that gamma 5 is that one?
Yeah.
And that the left-handed one should have a plus 1 eigenvalue?
Yeah, so if you PL has 1 minus gamma 5, so if you take that, what happens is that it knocks off this part. So the first, right? Yeah. Okay. So essentially, what I'm saying is that in the Weil representation, psi L has reduced rank, right? Or has fewer number of components. So this is the same thing as these two, okay? And similarly, psi r then is 0 psi r, right? So now, if I take the Dirac spinner in some arbitrary representation, not the Weyl representation, you can divide, you can have these two components and two components, but the first two components will not represent a left-handed Weyl spinner, right? So the Dirac spinner written cleanly in terms of a left-handed spinner and the right-handed Weyl spinner like this is only possible in the Weyl representation, right? In more general representation, this is the expression, this is the representation independent expression that you have to use. All right? All right, so now let's write out the generators. So what are the generators in the Weyl representation? Well, if you can show, it's a very straightforward and easy exercise, that it has a block diagonal right. So this is what we can call the left, the generator of the left, and this we can the generators of the right. You can show that these are also form the Lorentz algebra, but it's actually not a, what's the technical term? Not a faithful representation of the Lorentz algebra. All right. In the last 15 minutes, let's do some more explicit calculation. Let's figure out what the transformation for on the left-handed and the right-handed Weyl spinners look like. So just be careful. The word Weyl, the label Weyl is used in two different meaning here. A Weyl spinner is a two-component spinner, which you get by projecting the Dirac operator up down to the one of the eigenspaces of gamma 5. So that's so this Weyl spinner is a geometric object which does not depend on what representation you're using for your Dirac matrices. And then the Weyl representation, and I'm going to try to use the chiral representation for this, that's actually a specific representation of writing out those matrices, in which the Weyl spinners and the Dirac spinners have a very nice and clean relationship. Okay. Okay. So let's see how these how the Weyl spinners transform. So let's start with the Dirac. So I'm just putting D to emphasize this Dirac. And under a Lorentz transformation, it transforms like so. And then let's just take, for convenience, the parameters of the Lorentz transformation to be small. So I can just expand up to linear order. So up to linear order, it's 1 minus I omega 0 I. There was a half, but that half cancels out here because there's 0 and an I0. And then minus I by 2 omega ij, sigma ij. And this is acting on psi of d. Now, if I plug in my expression for psi of d in terms of psi L and psi R, the left-handed and the right-handed guys, and if I plug in these expressions in here, and I use the Pauli algebra, then I find this very simple looking expression where psi L, the infinitesimal, is so where by beta I mean omega 0 I. So beta is a three-component vector. These are the parameters of the boost. And omega ij, I mean the three angles for rotation. So note that there's an I here and there's no I here. So in some sense, sigma by 2, it acts as the generator for both rotation and boosts, but dressed with an extra factor of I. Okay? So these are the boosts. And these are the rotations. Okay?
That's the part that makes non-unitary, right?
Right, exactly. Because this doesn't have I, so that means that this transformation is not unitary. Whereas if you had just rotations, that would be unitary. Yeah. And so this is known as the 0 representation. Of the Lorentz group, which nobody, well, I guess when we came here, we implicitly switched to 4 dimensions back again, right? So we are in 4 dimensions. So this is the 0 representation of the double cover of the Lorentz group, which you can show is actually SL2C. So similarly, psi r, just from this equation, you can show that this is 1 plus beta dot so this is the spin 0, half representation. So I'm going to end by a very important observation, is that you cannot get this representation from this representation by doing a similarity transformation on your representation. If two representations are connected by similarity transformation, then they're equivalent. But there are no similarity transformation connecting these two things. And that's why they are inequivalent. It's just saying the same thing that we said over there in a different way, right? And you can explicitly show this. By noting that if you sandwich what the gamma matrices between, sorry, the Pauli matrix is between Pauli 2, then that actually is equivalent to taking the complex conjugate and multiplying it by -half. So by using this, you can try to construct psi r from psi l, how psi l transforms. And you will see that you will fail. That either you can get this term or that term, but you can't get both terms. Okay? So, that's done in the lecture notes, so I'm not going to go over it. In the last 5 minutes, I'm just going to, I probably will have time. Okay, let me just, right. Okay, so what you can show is that if you take the complex conjugate of psi of L and you multiply it by psi 2, then so you take that equation, the one where psi L transforms, you take the complex conjugate of that and multiply it by psi 2 on the left, then you get 1 plus beta dot so in other words, sigma 2 psi L star is a right-handed spinner, right? So yeah, so this is, sorry, I misspoke earlier. However, to get the right-handed spinner from psi L, you had to complex conjugate that. So that is clearly not a part of the similarity transformation. And because you have to complex conjugate it, complex conjugation is, it's actually not that's why it's a different representation, okay? So this is my physics way of proving that this representation is related to this representation by complex conjugation. And not similarity transformation. Okay, in the last minute, oh, I have 3 minutes, okay. Let me tell you what happens in odd dimensions. Remember that when we develop the Dirac dimensionality of the Dirac algebra, we work in even dimension. For odd dimensions, let's just concentrate on 5. Suppose we lived in 5 space-time dimensions, Kaluza-Klein theory and all that. Then what would you do? Then you would need 5 Dirac matrices. 0, 1, 2, 3, 4. And sorry, this is not 0, this is gamma 0. So there are some typos in my lecture notes here. And gamma 4, if you define gamma 4 to be I of what we defined to be gamma 5 before, then you knew that gamma 5 anti-commuted with all these gammas. So if you define gamma 4 in this way, then of course your 5-dimensional Dirac algebra would be what you want it to be. And I put the I here because gamma 5, as we defined, was a Hermitian matrix, but gamma 4 has to be anti-Hermitian, right? So this would be your new Dirac algebra, your set of Dirac matrices. And now you can say, okay, can I define a new gamma, say call it gamma tilde, such which it would be this thing. So if you work this out, you will see up to a psi, up to some plus minus or I, it's the identity matrix. In other words, in 5 dimensions, you cannot construct the analog of gamma 5, and that the Dirac representation in 5 dimension is actually not reducible. Okay. What about the dimensionality of the Dirac representation? The dimensionality of the Dirac representation in 5D is the same as the dimensionality of the Dirac representation in 4D. And why is that? Remember, when we constructed the representation theory of this, we paired these up. into the raising and the lowering operator. But this guy doesn't have anyone to pair with. Therefore, you cannot construct a new creation and annihilation operator for gamma 5 that is independent, that is independent of the others. Therefore, all of what we have done exactly goes through in one higher odd dimension, but we say that the dimension of the Dirac representation is 2 to the power, the integer part of d by 2. Okay? Because the integer part, even if d is 5, it's still 4-dimensional. Okay? So in 6 dimensions, what would be the dimensionality of the Dirac spinner? 8. What about in 7 dimensions? It will still be 8. Another corollary of all these of this observation is that in 5 dimensions there are no left-handed or right-handed well spinners, because there is no object such as gamma 5. So the idea of this is called chirality, gamma 5. The idea of chirality only exists in even dimensional spacetimes. And yeah, I'll stop there.